Ever wondered how an AI like ChatGPT actually learns? Well, at its very core, the entire incredibly complex training process is really about solving one giant puzzle. It's an optimization problem. You see, when a neural network is first born, so to speak, its brain is a complete blank slate. All of its internal parameters, these millions of little dials we call weights, are just set to random numbers. At this point, the model is totally useless. It knows nothing. So the whole game, this process we call training, is really just a massive methodical hunt for the one perfect combination of those weights that turns the model from a random jumble of numbers into something genuinely intelligent. And that journey from random to refined is exactly what we mean when we say that training is just optimization. It's about finding the absolute best solution out of trillions upon trillions of possibilities.
Okay, so here's how we're going to break this down. First, we'll get a feel for what this optimization journey actually looks like. Then we'll dive into how this applies to large language models in 3 very distinct stages. All right, to really get this, I want you to picture a giant, hilly landscape in your mind. I'm talking endless mountains and deep, deep valleys.
This terrain has a name. It's called the loss landscape. Now, every single point on this landscape represents one possible configuration for our model's weights, and the altitude, how high up you are, represents how wrong the model is. So up on the peaks, the model's making a ton of mistakes. Down in the valleys, it's getting things right.
Our brand new random model starts somewhere high up on a hill. We'll call that starting point 𝗨0. The goal, the only goal, is to get to the absolute lowest point in the deepest valley. We call that perfect spot 𝗨*. That's the set of weights that gives us the smallest possible error. So how do we guide our model down the hill? I mean, we can't just let it wander aimlessly. We need a set of rules, right? We need a way to measure our mistakes and a way to know which direction is downhill.
First up, we need a scorekeeper. That's our loss function. It's a bit of math that looks at what the model predicted, compares it to the right answer, and spits out a score. A really high score means a big error. A low score means we're getting close.
And honestly, this entire massive undertaking can be boiled down to this one little formula. All it's saying is find the set of parameters theta that gives you the lowest possible average error across all your data. That's the name of the game.
And we play this game using algorithms like gradient descent. It's basically a loop. The model takes a guess, the loss function gives it a score, then a little calculus points us in the steepest downhill direction. We nudge the weights just a tiny bit that way, and then we do it all over again, millions or even billions of times. Now, this is where it gets really fascinating for large language models. It's not just one optimization problem. It's actually a sequence of them, stacked right on top of each other. And it all starts with a massive phase called pre-training. So, what is this first giant hill the model needs to get down? What's the fundamental problem it's trying to solve? The objective is, believe it or not, deceptively simple. Given a string of words, just predict the next one. So if you give it "the cat sat on the model's entire job is to learn that Matt is a very, very likely next word. This is our first optimization problem. The model's goal is just to minimize its prediction error over basically the entire internet. But by getting really good at this one simple task, it's forced to learn everything about language, grammar, facts, logic, even a bit of common sense. The result is a powerful model, but it's not yet very useful. It can finish your sentences perfectly, but it won't actually answer your questions. Okay, so our model understands language, but it doesn't know how to be a helpful assistant. That brings us to our second optimization stage, supervised fine-tuning, or SFT. So, new stage, new optimization problem. What are we trying to minimize this time? The goal now shifts from prediction to imitation. We feed the model a high-quality data set of prompts paired with perfect human-written answers. And the new optimization goal is simple. Make your output look as much like the human's answer as possible. And this example just shows the change perfectly. Before this stage, ask about gravity for a kid, and you get a textbook definition. After SFT, it's learned the style of being helpful. It's been optimized not just to be correct, but to actually follow instructions and be useful.
But just imitating isn't enough, because some answers are simply better than others. This brings us to the final and most complex stage of optimization, aligning the model with what we humans actually prefer. This is where you hear about RLHF, or reinforcement learning from human feedback. It's a whole little dance. First, humans rank different model answers, just saying, I like A better than B. Then, we use that data to train a totally separate AI called a reward model to basically act as an automated judge of human taste. And finally, we use that judge to fine-tune our LLM. The new goal? Generate answers that will get the highest possible score from that judge.
The algorithm that powers this step is often one called PPO, and its secret sauce is that it's careful. It pushes the LLM to get those high reward scores, but it does it in small, stable steps. It has safety rails to make sure that while it's learning to be more helpful, it doesn't just forget how to write coherent sentences.
Now, PPO is a classic, but this space is moving at lightning speed. You'll hear about newer, more efficient methods like DPO or GRPO. You don't need to memorize the acronyms. The point is, they're all just different tools designed to solve the exact same fundamental optimization problem. How do we make this AI behave in a way that aligns with what humans actually want?
So let's just zoom out for a second and look at this entire journey from a completely random state to a polished, helpful AI. And this is really the key takeaway. Building a modern LLM isn't solving just one problem, it's a whole sequence. You optimize for prediction to get general language skills, then you optimize for imitation to learn how to follow instructions, and finally, you optimize for human preference to make it aligned and helpful. It all comes back to this one central idea. The entire process is a guided tour through that massive landscape of possibilities. We start with a bunch of random, useless weights, our 𝗏0, and through this series of optimization problems, we carefully guide it to find the best possible configuration, our 𝗏 star.